Pay special attention to this paper. It is not a paper by Google or DeepMind or Meta or anything like this. Yet I believe it is a really important paper. It discusses typical sampling, which is a new decoding strategy of how we sample from language models. We usually train language models with a maximum likelihood objective that put a lot of weight on very likely words. And when we use these models to produce language, we either explicitly or implicitly reproduce that. We make these models sample very highly likely strings, which are boring and not human-like. It's not what we do. I don't say things that are just highly likely because I actually want to say something interesting. And that means that every now and then, I should utter something that's less likely. I should speak a word or a sentence that you didn't expect, because that's what transmits information. Typical sampling does exactly that and does it in a principled fashion. This video right here is a description, a review of the paper, and the next video is going to be an interview with Clara Meister, the first author of the paper. Both videos, but especially the interview, are super duper interesting. I would definitely invite you to check them both out, and I would definitely invite you to try out typical sampling. It is in Hugging Face, and whenever your objective is to sample something that is very, high quality, but also diverse and interesting, and not just bland high likelihood text, then that is your method for you. I believe that we do need new sampling strategies, and this one is very promising. Check it out, leave a like, and see ya. Hi, let me quickly tell you about Fully Connected, which is a curated space for the applied ML community. It features articles, project reports, news, events, and anything you could want. Especially the projects page acts as a little bit of a product hunt for ML, so feel free to add your own project right here. It's curated by weights and biases, but I know what you're thinking. Yeah, another company, blog, whatever, about their products. But this is not at all about weights and biases. It features some of their stuff, of course, but it is generally a really good resource to get good information on what's currently happening in deep learning. They have great articles and tutorials, like there's one on solving Wordle with reinforcement learning, which is pretty cool. There's one explaining group normalization in PyTorch, and there's one that explains to you how to run YOLO v5 object detection on Windows. So as you can see, they have all kinds of stuff, and the list of already existing articles is long. If you still don't believe me that it's not all weights and biases, in fact, you can submit a post there. You can click the button, write a post, it will be reviewed by them, and then published. So one of the coolest ML startups currently is going to push your content. How great is that? Now, if you are just a lurker like me, then, head over there and subscribe, because it's user submitted but curated, so you get the best of both worlds. Besides articles, they also have events, which usually means they're webinars about various topics. You can look at old webinars, but you can also subscribe to get updates on new ones. They also host their podcast there, Gradient Descent, and the current episode is actually with Jensen Huang, the CEO of NVIDIA. So pretty big hitter. And lastly, it includes the good old Weights and Biases community forums, where you can get all kinds of help on Weights and Biases products and beyond Weights and Biases to all kinds of things machine learning related. So again, Fully Connected, it just got a major redesign. Please check it out. Go over there, subscribe for awesome articles and news. There's new stuff all the time. Thank you so much to Weights and Biases for sponsoring this video. They've been a great sponsor, so please check them out. That's 1db.ai/fully-connected. And now let's get into the video. See ya. Hello there. Today we'll look at Typical Decoding for Natural Language Generation by Clara Meister, Tiago Pimentel, John Wiher, and Ryan Cotterell. This paper suggests a new way of decoding, of producing text from a large language model or a small language model. It doesn't matter. We don't discriminate here. In any case, usually, currently, you might have heard of things like beam search. You might have heard of things like Nucleus sampling and top K sampling. These things are all right. And interestingly enough, the stochastic methods like Nucleus and top K sampling are better than the methods that try to find the most likely things, such as beam search or greedy decoding. However, it's still not satisfactory. Large language and small language models, they often produce text that is boring, just kind of bland when you actually use them, even though they have amazing perplexities on text. This paper tackles this. It proposes that when humans generate text, they don't just produce the most likely text, they will actually trade off likelihood with information content or the transmission of information to another human. And that trade-off can be captured in the frameworks of information theory. And we can generate, or we can suppose, a decoding scheme which they call typical decoding, typical sampling, which exactly encapsulates that notion of balancing interestingness or information with likelihood. And when they test it, that actually results in better results. This could be really crucial because it doesn't require any change to how we train language models. In fact, we can take off-the-shelf trained language models and simply use this new decoding strategy out of the box, and it applies across domains. Now, I have long said that we need that probably our decoding methods, our sampling methods, may be inadequate depending on what we do with those language models. For example, AlphaCode samples a whole bunch of programs in order to solve a problem. Now, there is value in diversity if you sample a whole bunch and then after that use like a filter to narrow it down. So I think depending on what you want to do, maximum likelihood sampling is very appropriate. This paper, for example, mentions natural or machine translation, because in machine translation, you really want kind of the best translation for a given input. However, in other frameworks, such as AlphaCode, but also such as storytelling, this paper mentions summarization maybe as well, we want to trade off some of this maximum likelihood for some more diversity or for some more interestingness or for some more information content. And that's what this paper does. So we'll dive into it. If you like content like this, as always, leave a like and don't be shy to let me know in the comments what you think. I'm not entirely sold on what this paper does. I do agree we need different decoding strategies, but I do have my reservations about this exact one. So let's dive into the paper. The paper first complains about the exact thing I complain about, namely saying that language models currently, they have extremely low perplexities on corpora from many domains, yet when used to generate text, their performance is far from perfect. And by that they mean they produce text that is undesirable, e.g. generic or degenerate. Wait, yes. So either generic or degenerate, or just, as I said, boring, bland, and that comes from the fact that a lot of these things, they try to find the maximal probability string. So they think, I'm going to sample from the probability distribution and I want to sample what is the most likely, because that's how we train these models, right? So let's do a short excursion. If you are unaware of how language models are trained, they're usually trained, you have a sentence like, the cat is in something, the house, and it goes on. So what you do is you input a part of the text and then you let the model predict the next token, and then you input that part and you let the model predict the next token. Now in training, this is all good and fine, but at inference time, what you do is you provide a prefix, for example, the cat, and then you have to decode here. You have to decode a word, what's next, and then you feed that, whatever you decoded, into the language model, and you decode the next word.
And I think that's where part of the problem comes from, because during training, naturally, what is here is given by the data set. So every new step that you take, if there is something unlikely, if there is a certain diversity to the input, that's captured by the training data. However, in decoding, you sort of make your own data as you go along here. And if you just always focus on finding very likely next tokens, you'll never get into kind of a less likely environment, which could also be correct, right? So that is one of the problems. However, obviously, in these language models, the way they work is, for example, you input all of this into a big model. There is some sort of a model, which usually is a transformer nowadays, and out comes a probability distribution. And the probability distribution is over your vocabulary. For example, there is the vocabulary is cat, dog, I don't know another word. What's another word? House, something like this. And it will give you a distribution of probabilities over these words. And you can now choose what to do. Either you can take the maximum one, which often if it runs into these problems of being boring or even repetitive, you can sample from this distribution, which is also not super appropriate because, and the paper touches on this a little bit, because sometimes the what's called the long tail here, there are many, many words, of course, and they all have some probability. And you don't want to get into these super low probability words because they might just be artifacts of the model. The model doesn't represent these low probabilities really well. It's really good at the sort of high probability words because, well, it's essentially trained as a classifier. And the classifier is trained to give you the correct label as the highest class. And it doesn't really care about the rest of the words, especially not the ones that have a really low probability. So what people do is they came up with, first of all, beam search. What beam search does is it considers multiple futures. So if it's here, that cat, like that cat, it considers multiple futures and it looks a few steps ahead. So it looks a few steps ahead and it keeps a list of things that are possible to complete. So for example, in the beginning, it goes all these 3 routes and it keeps those in mind, along with the probabilities that you go along that tree. And then, you go ahead and maybe the buffer is 5 large, right? So now we can still fit it because there's 1, 2, 3, 4, 5 paths currently. But as soon as we expand the 6th one, this one here, we have to drop someone. So we consider all the paths and we consider only the ones with the highest likelihood so far. These we can simply do by multiplying the probabilities of consecutive decoding steps. We consider the most likely 5, let's say, paths so far, and we delete some of them. Let's say that this one here is really low probability. And then once we add this one here and this one, we have to drop another few. So let's say this one, these 2 here are really low probability, and so on. And we only continue the paths that have good probabilities or high enough probabilities to be the highest possible. That's beam search. And the reason why people do it is because there might be a very high likelihood sentence that you could produce, but the next word just happens to be low in probability, right? Maybe here, house will lead to a sentence that down the road is very likely, has a very good score. But just this word right now, in this case, is low probability because the immediate best word would be dog for all the possible continuations, or for this particular prefix for all the possible expected continuations. So beam search is even worse than greedy decoding in the sense that it really finds the high probability stuff. It doesn't, and it looks ahead to be even more accurate. If you go to the opposite end of the spectrum, you can say, okay, can we sample, but can we fix the sampling issues that arise from this tail? And that's why people do 2 things. So there's top K, top case sampling, and there's nucleus sampling. And they both work pretty much the same. So top case sampling, what it does is you have, again, your probability distribution. And top case sampling simply says, well, can we only consider the k largest entries in that distribution and then just sample from that? So let's say k equals 3, then we only consider the 3 largest entries here, and we just forget about the rest, and we only sample from that. We have to renormalize, but that's fine. And then nucleus sampling is very much the same, except it says, well, I'm going to afford myself a probability, a cumulative probability of let's say 0.7. What does it mean? It means that this distribution right now has a cumulative probability of 1. I am simply going to take the largest ones, like, okay, this one, and this one, and this one, until the cumulative probability reaches my maximum threshold. Maybe I'm going to take this one as well. You can see the advantage here is that you don't always pick the same amount, but you always pick sort of the top entries that make up, let's say in this case, 70% of the mass. And that is useful because you have to consider multiple scenarios. One scenario is where the distribution is very peaky, like there you only want to consider very few entries. So you only want to consider few entries because everything else is just really unlikely. However, if you think of a distribution that is more spread out, like this one, then you want to consider more entries because all of them are kind of likely. And nucleus sampling affords you that, whereas top case sampling would just disregard the shape of the distribution and pick the top ones. All right, so these are the decoding strategies, but still you can see they always go to the top or the most likely things. And this paper says, well, that's kind of dumb. And it shapes this as a information theoretic problem. So we already said that humans probably want to trade off the likelihood of a string, so like how likely it is to appear, meaning essentially how much it is expected, because if I just say things that other humans expect, right, then I'm essentially not transmitting much information at all. So we can say that every string has a form or a content of information. Actually, I'm going to skip here to the theory section directly, and forgive me, I've pretty much explained all of what's highlighted already. So what we can say is that a y is the message that you want to pass. So let's say it's a sentence. The information content can be quantified as its negative log probability. Essentially, the less likely a given message is, you can see here that's negative log probability. The less likely a message is, the more information it carries. You have to think of it like exactly as I said. If I say something that's very likely, the other person, could have expected it because it's so likely. It's like if you meet the stereotypical boring person, or if you see a movie where it's like a really stereotype of a boring person, they will always say exactly what you'd expect them to say. However, if you say, let's say you communicate with someone and they all of a sudden say something that you really didn't expect, now that's a lot of information right there. In fact, you can, by simple application of the chain rule, you can also define a information content for every single word in the sentence, and that is going to be just the conditional log probability, the log conditional probability of that word given the prefix, and that's the prefix, those are the previous words in the sentence. So akin to the information in a sentence, a word carries a lot of information if you really didn't expect to see that word as the next word in the current sentence that you begun, or that your conversation partner has begun to say. So we carry this through, and the assumption here is that the goal of an agent is to transmit information efficiently while also minimizing the risk of miscommunication. So that's the fundamental trade-off that humans do when they communicate. At least that's the hypothesis. If you transmit a lot of information, you're going to have to utter some words that are very not likely, because that transmits a lot of information. However, if you overdo that, and if you, for example, don't follow the rules of grammar anymore and just send around low information messages or high information, low likely messages, your receiver will be confused because they don't know what to make of it, because they really didn't expect to see something like this, and therefore there is a chance of miscommunication. You can imagine that if you want to transmit a message to someone, right? If you want to explain something to someone, you always have to adjust to what they already know. Like if I want to explain the chain rule to someone and I expect them to already know a little bit of math, I'm going to transmit a lot. I'm going to have to adjust my message to that. And if I assume too much of what they already know, and then I'll just end up saying something like, oh yeah, if you derive f of g of x with respect to x, then you have to, well, you just derive g and then you kind of multiply by the derivation of f, and it's all good, right? It's all good. So sorry for this butchering of the chain rule, but you can imagine that someone who has little grasp of math in the first place would be very, very hard, because I only utter the words that carry so much information that are so not likely in their framework that there's a chance of miscommunication. I don't know if actually that captures it the best. Maybe there's a better example, but that's sort of how I think of it. What they do define, and now we get into the decoding strategy, is the expected information that a specific symbol in the message will contain. So this formula right here, you might recognize as the conditional entropy of a given word in the sentence, namely, and this, I think the notation here is a bit out of place. I think this should be something like the expectation of the information content of just the t-th word, not necessarily y of t, because y of t, we sum over y of t right here. So so we ask ourselves, if we have already produced the sentence up to time step t, and we consider the distribution of words conditioned on this sentence. So we ask our language model, what's the distribution of words that could come next? And we ask ourselves for each of these what's the information content? And since we have the information content is the negative log probability, that's this, and here is the minus sign. And we ask ourselves, so what is the expected information content of the next word? Whatever the next word is, what's the expectation of its information content if we were to just sample from this probability distribution? And then this here is the formula, right? We simply multiply whatever we're interested in, which is the information content, with the probability, and we sum that up across the set that we're interested in. It's just the definition of the expected value, and by happenstance, it is also the definition of the entropy or the conditional entropy. So the expected information content of any given position in a sentence is the entropy is the conditional entropy of the distribution at that point. So what does that mean? That means if my distribution is very peaked, so if it's very likely that one of these three words here is uttered next. So if I find a text somewhere, right, and the sentence up to here was something, and then there's only like three words that could potentially be there, none else. It's a very peaked distribution. That essentially means the entropy here is very, very low, and therefore the information content of whatever word comes next is probably going to be very low, because all these words are super likely. However, if the distribution is very shallow or very broad, then the entropy is high. And you can also see, since any of the words that could come next, first of all, there are many more that could be considered, and all of them have less of a likelihood. Therefore, the negative log probability will be higher. So any of those words will have more information content, and especially the expectation over those words, the information content will be higher. So that is just the definition of the expected information content. Now here's the hypothesis of this paper, and they base this on some psychology theories or linguistic theories, but here's the hypothesis. Any given word should have an information content close to the expected information content, i.e. the conditional entropy given prior context. In other words, we expect the difference between the expected information content and the true information content to be small in human-like text. So the hypothesis here is that the way humans balance this trade-off between interestingness and likelihood, and so in between information transmission and not being misunderstood, is that they implicitly calculate the expected information content of the next word, and then they try to choose the next word in accordance so that it is as close as possible to that expected information content. So when I talk, I model sort of the transmission channel to my receiver, and I figure out, okay, in the language right now, what would be the expected information content of the next word? And then I try to match that as closely as possible. And that gives me a way of determining this trade-off. Again, this is a hypothesis. It's backed up by a few theories from linguistics. This is also known in information theory as typicality. So a typical message is one that has the information content of that is close to the expected information content. But we'll investigate. So they say figure 1 shows for human-generated text the distribution of this epsilon. So this epsilon is the distance between these two quantities, the expectation and the actual thing that's uttered. Remember, the expectation considers all possible next words and calculates the expected information content of them. And then this thing right here, this thing is just the information content of the next word that is actually uttered or actually written. So what would we expect this, or what do we see if we analyze human-generated text? And these are obviously language models that estimate the probabilities of these words, but these are evaluated on human-generated text, so not on language model-generated text. Because remember, this paper is all about how do we do that in order to not make the mistakes. So let's look at what humans do, and you can see the distribution is very peaked. Now, this isn't the distribution of words, this is the distribution of this epsilon. So that essentially means this distance, this difference right here is very, very peaky. And it's peaky around a very small value. You can see here the scale goes from whatever, -10 to 20 or something, and the peak is at a value that's quite close to 0. Now, it's not exactly 0, but this is empirical data. So this paper says this is evidence for the fact that humans do, as much as they can, try to match the information content to the expected information content. Now, it'd be interesting to see what you would actually, let's say humans would just sample from the distribution itself, right? What kind of distance between the entropy and the information content would you expect to see? Maybe a Gaussian or a log Gaussian. I'm not entirely sure. Also, what is peaky? What does peaky even, like, how do you characterize peak? Like, I can see peaky, but it's proof by picture almost. And then we see a very interesting imbalance, namely there seems to be sort of mass going higher up, always on the left side of this, rather than on the right side. There seems to be a bit of a longer tail on the right side, but a bit more heavy mass on the left side. Now, what does that mean? This is, well, I can't really make sense of it, because this is the epsilon is characterized as an absolute value, whereas this right here is not an absolute value. And so I'm going to guess they left away the absolute value. Therefore, I don't know the distribution of the deviation of information content from the conditional entropy per token. Okay. Again, I do not know what came first, if they do h minus I or if they do I minus h, and that determines how we interpret these plots. So I'd rather not interpret them in the wrong way right here. So that's what they say. The peaked nature of the distributions reveals that humans indeed tend to form language with per word information content quite close to their expected information content, and the centering of these distributions around a value close to 0 reveals that our probabilistic language generators are learning what this rate is. Well, I'm not sure I agree with that statement, because being peaked doesn't mean like you need both to be true at the same time. If you assume that the language models are really good at what they do, then you can claim that humans peak around 0 and therefore they match the expected information content. If you assume that humans match the expected information content, then you can conclude that language models are really good at what they do, because the peak seems to be rather around 0. But you can't draw both conclusions at the same time from this plot, because you need one to justify the other. In any case, this is a minor point. What is interesting is that here, they go into information theory, as I said, this notion of typicality, which is exactly what we're describing right here. It says typical messages are the ones that we would expect from its probability distribution. Their average per symbol information content is close to the entropy rate of their source distribution. Now, the interesting observation right here is that the definition implies that the highest probability message is often not a member of this set. Its average information content is too low. So if we consider any distribution and we consider what's the expected information content, which is the way we defined it, and we only consider messages, let's say these are the messages, we only consider messages that are close to that expected information content. But those are going to be messages that are kind of somewhere in the middle of the likelihood. So they're not super duper unlikely, because the expected information content is, again, the expectation over all of these messages, which is going to be not super duper high, which makes these rules out these unlikely messages. These are prone to misunderstanding, but it also rules out the very likely messages, because those are going to be prone to being boring and not transmitting any information at all. And that is something interesting. That is exactly the property we want in a new decoding method. Leave away the really low likelihood stuff and leave away the really high likelihood stuff, because that's boring. The typicality is a property. Okay, now they go into why we have to go for a local notion of typicality, whereas information theory usually defines it as a property of the entire sentence or of the entire message. I don't necessarily want to go into that. The next chapter, they try to justify this with psycholinguistic concepts. There are two they consider. There's the uniform information density hypothesis, which proposes that speakers construct their utterances such that information is distributed uniformly across them. And the speakers choose words such that their information rate is closer to a target channel capacity, which is essentially what we're doing right here. Then there's the Rational Speech Act, and the Rational Speech Act it casts a speaker's behavior as the maximization of a utility function, and the utility function is a sentence's usefulness to its listener. So the way it constructs this, again, this is sort of hypothesis. It imagines this literal speaker. So this is a hypothetical speaker that just samples from the probability distribution. It just looks at the probability distribution and just samples from that. And it just utters the words as they come out. And that means, with the typical problems, like it's going to utter kind of low information stuff a lot of the times. Then it says, well, the pragmatic speaker, and that's what the humans would be, the pragmatic speaker produces sentences to maximize the utility function as opposed to following its expected literal behavior. If you define the utility function to be this thing right here, then the hypothesis kind of matches. This Rational Speech Act. However, I find this also to be a little bit shady, because if I have a different decoding method in mind, I can apply the same argument. I can simply say, well, my utility function is now my new decoding method. I'm not super convinced by this. However, it's interesting to see that people think in this way, that they say, well, there is going to be this literal imaginary agent that just speaks according to the distribution, and then there is the upgraded version of that, and probably the humans are a form of an upgraded version, this pragmatic speaker, that changes something, that sort of uses this distribution but changes something about it. And that's exactly what we do. So how do we do it? And we've already alluded to most of it. So what we do is we introduce this typical sampling. Much like Nucleus sampling, we define a threshold, in this case this is called tau, of probability mass that we're going to allow in our subset of words. So again, maybe we have a distribution of a couple of words and they have different likelihoods under our language model output, and we assume our language model output models these probabilities, especially the non-negligible ones, well. Then what we're going to do is we're going to calculate the expected information content, which is the expected negative log probability, which is also the conditional entropy. So we're going to estimate this property by simply calculating it. We can do this. This is simply, again, this is p of x given y times log p of x given y. The log probability is usually already output by our model in the form of logits. We just need to normalize it, and if we apply some sort of a softmax operation, we get the p of x given y. So then we have the conditional entropy, and then we simply choose the words that are most close to this. So maybe the expected, the entropy, let's say these are the log probabilities right here. Let's say the expected one is here. We simply choose in order the words that are most close to that one. So it would be this one right here. This is really close. Then this one is really close. Then, well, it's a tough choice. Maybe this one's really close, and then maybe this one's really close. And that we do that until, again, we reach our target probability mass. Again, if the distribution is very peaked, so if the distribution is very peaked, that means the typical information content is going to be lower, which means the words that have low information are going to be chosen more, and these are also going to be less words, and that gives us our original case back, where we're simply going to choose the highest likelihood words into our bucket to sample from. and that sort of regresses to the old case if the distribution is very peaky. However, if the distribution is flatter or more broad support, then the expected information content is going to be lower, which means that probably these highest likelihood ones are not going to be in it, and we opt for more interesting ones that are also likely but not as likely. Okay. So this kicks in mostly when there's a lot of possibilities, which you can see in, let's say, machine translation. There is not. In machine translation, it's often very clear, or there's only a few possibilities on how to translate something. However, in storytelling, there's lots of possibilities how things could continue, and there our distribution are much more shallow. And this method would exploit that by saying, well, I'm just not going to consider the most likely things right here. The computational complexity is the same as Nucleus or top K sampling. We also have to determine the set we're going to consider by somehow calculating across it. We have to aggregate it, we have to renormalize it, and then we have to sample from it. Except here, well, I guess we always have to sort, right? Yeah. Here we also have to calculate this conditional entropy part. It's the same in complexity, but it does add a constant overhead, or like a constant factor overhead to the whole thing. So the last thing I want to go in here is the choice of hyperparameters in this one. They say we found k equals 30 and n equals 0.9 to perform best. So these parameters perform best for top K and Nucleus sampling respectively. So this is for their experiments. So one is for top K sampling and one is for Nucleus sampling. For typical sampling, we found tau equals 0.2 and tau equals 0.95 to provide the best results for story generation and abstractive summarization, respectively. So while they allow for a single parameter for each of the baselines, they go with a separate parameter for different tasks for their method, which is a bit shady. Now, there's two possibilities. First possibility is they sort of stifled the baseline by only sort of giving it, not exploring well enough the possibilities. Or what I think happened most likely is that the same parameter performs pretty well for all the different tasks, which is a good property in itself, right? Here we consider 20% of the probability mass, and here we consider 95% of the probability mass. Now that's a huge difference in how our set looks, and that by itself makes it, in my opinion, a bit of a weaker choice for using this as a decoding method, because for every thing that I want to achieve, I need to essentially tune this parameter. Whereas with top K sampling, I could just leave it be. So it'd be interesting to see if in the future there might be, because I'm a fan of this technique in principle. So maybe in the future we can find more of an adaptive way, much like Nucleus sampling is an adaptive way of top K sampling. Maybe we can come up with an adaptive way of determining the number here, or the parameter of how many things to consider. So I don't want to go too much into the evaluation. There is a difference. Sometimes it's stark, sometimes it's not as stark. It is different in different regimes. You can see that depending on the regime that you are at, it's sometimes the different methods are really different. Sometimes they're quite close. Sometimes they switch places. Yeah, I don't want to go too much into the results because we can maybe discuss them in an interview. But qualitatively say, for example, for the summarization task, we see that typical sampling provides a comprehensive and coherent summary of the article under consideration. In comparison, Nucleus sampling leads to hallucinated facts. For example, getting drugs from under... Okay, I haven't read the article, but Nucleus sampling hallucinate facts, which is one property if you sample only from high likelihood things, right? You're just going to continue with things that are very likely in the language itself, rather than transmitting the necessary information. While top case sampling misses some of the important information in the article, e.g. the charges of burglary and arson. And that might be because top case sampling simply has this fixed bucket of words to consider, and as soon as one word is not in that bucket, it simply is forbidden from uttering it, even if the distribution is shallow and that word is kind of likely. So I want to stop here and just give a few thoughts on this. In my opinion, I already said it is quite needed that we have different decoding strategies to achieve different tasks. This one right here, it seems really interesting. It is a way to trade off sort of not considering the most likely things, but also not considering the least likely things. However, I'm not sure if the notion of the matching the expected information content is appropriate. I can't tell. It's a good hypothesis. I don't know if this quantity here, the absolute distance, is a good quantity. Like, why would it be the absolute distance? And the other issue I have right here, but this might be my ignorance of information theory, is so if I change, if I assume the humans talk like this, they choose their words according to the expected information content, right? And I use this particular construction right here. That is everything that comes out of this, whatever comes out of this will have a different expected information content than the original language, right? If I wanted to actually match, like if I wanted to keep the expectation, I probably couldn't do this just in absolute difference. That's probably going to change the expected information content, let alone the distribution of it itself, but just the expectation is going to change. Now, if you're telling me that humans do it like this, and that our language models are trained on text that is written and uttered by humans, like, wouldn't that text already have that property, and therefore sampling from it would be the original distribution? Or in other words, if I produce text like this, like, shouldn't I get the same distribution out that my language model predicts, because my language model is trained on human text, and your claim is that humans sample text like this. So why would that be any different from sampling from the language model itself? And especially, shouldn't it be that the expected information content remains constant if I apply this sampling technique? Just out of principle, because by definition, if it doesn't, then it doesn't match human generated text because that's already the input. That's the training data. All right, but maybe I'm sort of ignorant of information theory right here. My other concerns are with the hyperparameter choice, I'd be interested to dive a little bit more into this, like what would we expect to see with the different sampling methods or with different hypotheses. This is also really interesting, but I'm going to leave it at that. All I can say is that we should probably try this out, and maybe, for certain tasks where diversity and actually transmitting information is more important than being, uttering the most likely thing, this might really be a cool application, and maybe we'll figure out an automatic way to adjust the hyperparameters. Let me know what you think. Maybe you've already tried it out. You can give a little bit of a report on how that went, and I'll see you next time. Bye-bye.